In this video, I'm going to provide a brief introduction to the reaction types for coordination compounds, then review reaction progress curves and the information they provide, and then finally talk briefly about three broad types of reaction mechanisms for substitution reactions in coordination complexes. Your book discusses three broad categories of reaction types for coordination compounds, and these include the ligand substitution, redox reactions, so oxidation reduction, and then also ligand reactions, so reactions that happen to the ligands that are coordinated to the metal. Ligand substitution refers to the process of removing one ligand directly coordinated or bonded to the metal. For instance, one of these water molecules in the hexaaqua iron 3 complex shown, if we add SCN-, that can replace one of the waters, and this is called substitution. Now the SCN is directly bonded to the iron and one of the waters has been displaced. Oxidation reduction refers to transfer of electrons to or from a complex. And so, for instance, this iron 3 complex, if we add an electron, we can reduce it to the iron 2 complex. So there's the redox reactions of coordination compounds. And then finally, reactions of ligands. This refers to reactions of the ligands themselves that are coordinated to the metal. So undergoing some type of acid-base or redox type chemistry or other types of reactions. In this example, the zinc complex with 3 histidines, which are nitrogen donors, also has a water, which is shown in red, and that water ligand deprotonates and then inserts in a nucleophilic type reaction into CO2, and this produces hydrogen carbonate. This metal complex shown is part of an enzyme called carbonic anhydrase, which catalyzes the reversible production of hydrogen carbonate, which is important blood buffer. So it's important in maintaining blood pH. Redox reactions are also important biologically. Many of the electron transfers that occur in biological systems are through metal cofactors and proteins. So for instance, shown here, we see that many of the complexes involved in the electron transport chain, which is important for energy production and the eventual reduction of O2 to water in respiration, many of these complexes are metals. So for instance, you see here iron-sulfur clusters and hemes. Hemes are iron complexes with protoporphyrin, large protoporphyrin ligand. And then finally, at the end of that chain are some copper atoms. And those actually are involved in a reaction of a O2, which could be considered a ligand to the coppers and the hemes in the cytochrome C oxidase complex. So these are all important reactions. Of course, they find the reactions of ligands and the redox reactions and substitution reactions are all important in organic synthesis, inorganic synthesis, and so forth. Your book discusses these reactions in this order: ligand substitution first, followed by oxidation reduction and reactions of the ligands. And in particular, it hits ligand substitution in octahedral complex, so OH symmetry first, followed by ligand substitution in square planar complexes, so D4H symmetry. So we'll look at OH substitution reactions first. But even before that, we'll do a little bit of review of reaction energy profiles, or reaction energy progress curves. In these types of curves, usually free energy is plotted on the y-axis, or possibly delta H on the y-axis, and then extent of reaction or reaction progress is on the x-axis. And the progress, the energy profile, the progress curve follows the progress of the reaction from reactants to products. Or we'll use a simple sample reaction of the substitution of a ligand X with ligand Y. So Mx and Y are reactants, and My and the free ligand X are the products. On the left-hand side of the diagram are shown the energy of the reactants. On the right-hand side, the energy of the products. The overall difference in energy of the reactants and products will be the energy of the reaction. In this case, the products are lower in energy, and so this will be an exergonic reaction. In between the reactants and products is usually a barrier, a peak, and this energy barrier must be overcome in order to transform the reactants into products. And this difference in the reactants and products, delta G for the reaction, should not be confused with that peak, which is the activation energy, or the transition state free energy, delta G, and it's usually with a double cross at the top to represent the transition state. That transition state free energy, also called the activation energy for the reaction, and written as E sub A. The peak represents the structure of, or the energy of, the transition state. So somewhere between reactant and products. Okay, so for this reaction, we would write a rate equation as rate is equal to a rate constant K times concentration of the reactant metal complex Mx times the concentration of the incoming ligand Y. And of course the reaction progress curve shows this as a sort of one-step process going through a single transition state, so this rate equation is reasonable. K, the rate constants for the reaction, is related to the activation energy as shown here. It was called the Arrhenius equation. And in this equation you can see that as the activation energy increases, K is going to get smaller, and of course K directly affects the rate of the reaction. So the smaller K is, the slower the rate will be for any particular reaction. And this means that as the activation energy increases, so if we draw the reaction energy increased, like so, right? So larger activation energy will result in a slower reaction. So in other words, fewer reactants are going to have sufficient energy to overcome that barrier and go on to products, and that slows the reaction down. So K is related to the activation energy. As activation energy increases, K gets smaller, and this of course makes the rate of the reaction slower. You can also have two-step reactions, and that would be represented by this type of progress curve. In this case, we have transition state 1 and transition state 2. Since transition state 2 is larger, that is going to be labeled as the activation energy for the production of product from reactants. Oops, let's go back. And in the middle of the two transition states would be possibly an intermediate is shown in the trough, and that might be we might be able to identify that intermediate depending on its stability. So for instance, applying this to the reaction that we're using as our example, substitution of ligand X with ligand Y, this could occur in 2 steps. Step 1 would take the reactants to some intermediate, and then step 2, the intermediate would break down into products. And so for example, in this case, MX could have a dissociation first of the X ligand from the metal as step 1. That brings us to the intermediate. The transition state would represent the breaking of the MX ligand metal bond. Then formation of the intermediate, shown on the right, followed by a reaction of our intermediate plus the incoming ligand Y to produce the final product, which has Y coordinated to M. Transition state 2 would represent the beginnings of the formation of the bond, the interaction between the intermediate M and the incoming ligand Y. Rate constants for each step in this mechanism, K1 representing the rate constant for the first step and K2 for the second step. K2 will be smaller rate constant, and that step will be slower since the activation energy for that step is larger. So since EA is larger for step 2, therefore K2 will be smaller than K1, and step 2 will be the rate limiting step. Okay, so now let's go over some of the reaction mechanisms that are possible for a substitution reaction. So just do a generic substitution reaction shown at the bottom here, MLX. X can be any number of ligands. We're going to cover in this course primarily focus on 6-coordinate and 4-coordinate complexes. So X would be either 3 or 5. Small x. Large X represents the outgoing ligand, and Y represents the incoming ligand. So, of the possible reaction mechanism types, the first one discussed in your textbook is dissociative D mechanism. And in this case, we have a dissociation of the outgoing ligand X first to produce the MLX intermediate, followed by a second step shown here in which the incoming ligand coordinates to that intermediate, produce the final product. The second other extreme, I guess, of the mechanisms is associative. In this case, we're going to have an interaction between MLX, the complex, with Y to form a intermediate in which both X and Y, the incoming ligand, are coordinated to the metal, and then that intermediate would break down to produce the product MLXY plus X, the outgoing ligand. Notice in both of these there are intermediates, and these are also shown in the reaction progress curves, the deep troughs representing intermediates that could possibly be characterized. It's not always easy to characterize intermediates in these particular complexes. These are also shown as having the first step having a larger activation energy and thus possibly being rate limiting. However, that is not always the case for either. For both mechanism types, it could be the first or the second step that is actually rate limiting. In between dissociative and associative type mechanisms are the interchange mechanism, or I. And I'm showing in this mechanism ml sub x, that complex, plus y to form a weakly associated, the dot ml sub x with the x ligand dot y represents a sort of a loosely associated incoming ligand, and the degree to which that is associated with the complex actually results in different types of reaction mechanisms, or we characterize the reaction mechanism slightly differently. So if the Y assists in the reaction in this case, although it's not necessarily a direct bond of Y to the coordination complex, the level of assistance, right, in forming this sort of intermediate complex results in us characterizing the reaction mechanism as either interchange D, dissociative, or interchange A, associative. And of course you see that in the progress curve, the dip is sort of much more shallow to indicate that that is not an intermediate that we're going to be able to characterize. Now, if Y assists in the reaction to a large degree, then the reaction mechanism would be called IA, or interchange associative, and if Y assists very little, in other words, it doesn't assist much in helping the outgoing X ligand to leave the complex, then the reaction mechanism would be I sub D, interchange dissociative. Okay, so that's the introduction to coordination reactions and the sort of four basic types of reaction mechanisms possible for coordination complexes.